Hello everyone, am I audible and am I visible? Let me check. Everyone, am I audible? Yeah, I think I am audible and I am. So, yes. So, fine. So, hello everyone, welcome to Geeks for Geeks. My name is Shanu Gandhi, and today we will be continuing our lecture series, GATE series on computer networks. So, today the major topic of our discussion will be the previous year questions on routing algorithm, GATE previous year questions. So, let's see what is the index for today. So yeah, today's index is nothing much more than the gate previous year questions. Today we will not discuss any concepts, but we will solve the questions and the concepts that are required in the questions. I will teach you at on the go. Also, I had already covered whole of this routing algorithms topic in this week's video, last 4 videos. So you can, if you want, you can go through that videos beforehand to better understand this gate previous year questions, or you can also watch this video too directly because I will be giving enough information just to understand the questions. So let's start the questions for GATE CSE in this routing algorithm. So yeah, let's start with our first question. So just try to read the question first and then we will try to understand and proceed with the solution. So this question was asked in GATE CSE 2014. Let me select a pen. Probably. Okay. Fine. So this question was asked in GATE CSE 2010, and the question is like that. Consider a network with 6 routers R1 to R6 connected with links having weight as shown in the following diagram. So this router has the network topology is given to us in the question along with the edge weights. Now, what was the question? All the routers use the distance vector based routing algorithm to update their routing tables. So it is also given that all the routers use distance vector routing algorithm. So distance vector routing algorithm is a routing algorithm in which the distance vectors are exchanged among neighbors and it is based on the localized knowledge. So distance vector algorithm is used to update the routing tables. Each router starts with its routing table initialized to contain an entry for each of its neighbor with weight of the respective connecting link. So initially everyone just knows about its distance to its neighbor. After all the routing tables stabilize, how many links in the network will never be used for carrying any data? So that is the main question. After all the routing tables have been stabilized in sense the distance vector has been converged and we have reached a solution that is optimal. And also how much steps are required in case of distance vector algorithm to stabilize. If there are n nodes, then there are n minus 1 steps required. N minus 1 rounds are required of exchange in order to get optimal solution. And on what algorithm this concept is based on? This algorithm is based on the concept of Wellman-Ford algorithm. So according to Wellman-Ford, this distance of routing works. So what are they actually asking now? Let us see this. They are asking that after this algorithm has stabilized, how many links in the network will never be used for carrying any data? So actually what they are asking is they are asking about the redundant links. The links that are redundant and that will never be used in any exchange of data. So suppose this question can be asked in many ways. First of all, let's try to see the simple solution that the question has asked, and then we will try to see the variations. So first of all, as we are given that the routing tables are stabilized, what does this mean? That they are at their optimal state. So in order to get the optimal state and distance, you need not to perform actually Bellman-Ford. Because if you will perform actual Bellman-Ford in this, so what will happen? There are 1, 2, 3, 4, 5, 6 nodes, and you have to perform 5, 6 minus 1, 5 times of 5 rounds of this algorithm, this distance vector routing, 5 rounds of this, and each round you need to, what you need to do, you need to create distance vector first of all for each of the node. So suppose this R1 is the node, and for R1 what will be the distance vector? There is the distance vector contain three things. The routing table contains three things. First of all, destination, then the distance vector or distances, and then the next hop. So for R1, each one has R1, R2, R3 up till R6. So what we have in this? So initially when just we are on our first round, then we at that time we only know about the distances of our neighbor and our own. So R1 to R1 is 0, and R1 to R2 is 6, and R1 to R3 is 3. Rest all are infinity. And next hop is R1 to R1 is R1, R1 to R2 is R2, and R1 to R3 is R. So this is how the actual table is prepared for all of them. For all of them, this kind of distance the tables are prepared, and then these tables are exchanged. Everyone exchange these tables with everyone else. So these exchanges are performed. And how many exchanges will be done now? So as you can understand, there are suppose there are 6 nodes. So every node will exchange a table with its neighbor, and it depends on how much neighbors they are having. So if it is a fully connected graph, then they will have a lot of neighbor, but as you can see, it is not a fully connected graph. So R1 and R2 will perform exchange, R1 and R3 will perform exchange, R2 and R3 will perform exchange, R4 and R5 will perform exchange, and R2 and R4 will perform exchange, R3 and R5 will, and R2. These are a hell lot of exchanges. So actually doing this distance vector will not be efficient for solving this question in gate. What you can do is to use your intuition, and what you can do is use your intuition to find the shortest path if the graph is small and simple. You can do that. So how can you do that? You can just look at any router, and you can try to find the minimum distance to every other node in the router. So what do we need in the end? In the end, we need the distances from each router to every other router, the minimum distances. So in the end, after the completion of distance vector algorithm, we get distance vector at each router, which is the minimum possible distance for each node to every other node in the system. So we can directly try to generate that distance vector if the graph is not too complex or big. So what we will try to see, what we can do here is we will directly try to solve this problem by our intuition, and we can check which links are not used anyhow. So that is simple. How can we do that? So what else you can do for for solving this problem more optimally is, suppose you are finding a distance for from R1 to R2, R3, R4, R3, R4, R5, and R6. But now what you can see is R2 to R1 is already created, R3 to R1 is also created, R4 to R1 is also created. So when you start with R2, you do not have to check for R2 and R1 now. So R2, R3, R4 and R4, R5 and R6 are enough. From R2, these distances are enough. And similarly for R3, just check for R4, R5 and R6. And similarly for R5. So you just need to check the minimum distances to the next nodes. And what you can do, you can just try to find out it by your intuition, and you can see which links are never used. So I had already solved this question, and I can also try to solve it again. Like from R1, what will be the distances and edges used? So from R1 to R2, you can see this edge is taking. Let me take different pen here. So from R1 to R2, this edge is taking 6 distance, but by this path we can reach R2 by 5 distance. So this R1 to R2 distance is 5, and the edges used are 3 and 2. So R1 to R2 is using edge 3 and 2. So what you can do is also maintain the edges that are being used in the optimal path, and in the end, edge that is not used in any optimal path, that will be counted in your answer. So from R1 to R2 we are using 2 and 3. So from R1 to R3, this 3 is used. R1 to R4, R1 to R4, you can see that 5 plus 7, this will be 14. Or what you can do is 3 and 9, 9 and 3 is 12, plus 1 13. So this is better, so we can use this one. So the optimal cost is I think 9 and 12 14, 9 and 12 and 1 13, and then optimal the edges that are used is 3 9 and 1, edge number 3 9 and 1. And similarly for R5, So I had already solved this. If I will try to solve, it will take a time now. So what you can we can directly see the solution, that which edges are being used in the optimal path, and you can what you can observe here is that one more important thing to observe here is that from reaching R1 to R2, you can use this direct edge or you can use this path, but this path is more efficient. So you will never use this edge. So this will be definitely a edge that will be. So R1, R2 is an edge that will be ignored. Also, to reach R4, once you reach R4 or R5, now you need to reach R6. So these two edges are required to reach R6. Now you can see that if you are at R4 and you want to reach R6, you can go through here 1 plus 4, 5 from R4 to R6. And even if you are at R5, you can just directly use this edge. So this edge is also not used any place. You can also try to visualize it by yourself. So these two are the edges that are redundant and that are the part of our answer. So the answer is 2, and these are the two edges that are redundant. So I had written a little theory also about this, and you can see that we can check one by one shortest distances and check for all shortest distances for Ri. We don't need to check its distance from R0 to Ri minus 1 because the network graph is undirected. So we have already created that value. So suppose shortest distance from R1 to R2, R3, R4, R5 and R6 is this. So distances is this and links used are this. For R1 to R2 it is this link, this link, this link, and this is how you need to note them down. And shortest distance from R2 to R3, R4, R6 is this. These are the distances and these are the links used, and you can just enumerate that links, and after enumerating that links you need to check which links are not used. So the links that are not used, if we try to mark them, then these two are the links that I already told you, R1, R2 and R4, R6. So these two links are not used, so the answer is true. So that was our first question. But also I one more thing that I need to tell you is that this was done by the fact, by utilizing the fact that we do not have to use any actual logic of distance vector in this algorithm. We just need to calculate the shortest path. But what they can ask in exam, if in order to check your knowledge about distance vector, what they can ask is, after two rounds of exchange, the distance vector of, say, root R5, R4 and R5 R. So they can also ask you in this way. They can give you tell you the number of rounds that will be only one or two. So two rounds you can perform. Just five rounds are more. 5 rounds are very high. But two rounds you can try to do and you can find solution for distance vectors. What will be the distance vector after two rounds of exchange or after one round of exchange? So this is the type of question they can also ask, and in this you cannot escape the knowledge of distance vector algorithm. You need to create this distance vector tables, the routing tables, and you need to exchange the distance vector among neighbors. So that is what also you need to know. So that was it for this question. So let's jump to our next question. So next question is also related to this question, as long as I remember. Yeah. So yeah, now what they asked is, suppose the weights of all unused links in the previous question is changed into 2 and distance vector algorithm is used again until all routing tables are stabilized. How many links will now remain unused? So here what they told us is that the links that were unused in the previous question, that was this R1 and R2, R1 and R2, and this R4 and R6. So they reduced this both's weight, and their weight is reduced to 2. Initially it was 6 and 8. So what will be now the links that are not being used? So yeah, this is an important thing, that sometimes what happens in the examination is some questions are related. Some questions are related, like question they will give question 31 as something, and the 32 will be continuation of this. So you have to attempt both of the question in order to get marks for second one or first one. You cannot do directly to the second question if they are related. So this is the kind of question that I am talking about. If you have not done the previous question, you cannot try to solve the second question. So in previous question, what did we find out? We find out the redundant links are this. Now, if we have not known the redundant links, we could not have been able to solve this question. So again, now what are they asking? They are telling that this links, the redundant links, the links that were redundant, their weight is increased. Oh, sorry, decreased. Now, after the weights have been decreased, what will be the links that will be not useful now? So what you can do is again simple. you can just change this weight as 2 and this link's weight as 2, and then you will again try to find the shortest path between each and every other node, like we did in the previous question. For R1, we will try to find shortest path from R1 to R2, R3, R4, R5, and R6. And we will check which edges are being used in these paths. From R2, we will try to find the shortest node path from R2 to R3, R4, R5, and R6. And we can use our intuition in that. So that is how this question is also done. So the answer is B, only one edge that is not being used. And the solution to this question is, you can check, you can verify, and you can try to find a better solution, but I don't think it will be possible. For R1, the distances to R2, R3, R4, R5, and R6 is this 2, 3, 9, 10, 11, and links used is this, and this. These are the unique links. Similarly, for R2, you need to enumerate the links, and for R3, R4, R5, and R6, you just need to enumerate the links. And after enumerating the links, what you can do is you can try to find a link that is not being used. So in this case, the R5, R6 link is not used in any shortest path. The R5, R6 link is what is the R5, R6 link? This 4. So now why this is so, you can just try to visualize is that even if we are at R4 or at R5, even we are at R4 or at R5, and we need to reach R6. So what is the cost now? It is 1, it is 2, and it is 4. So now if we are at R4 and we need to go to R6, we can directly use this. This is the best part, which is costing us 2. And if we are at R5, then also what we can do is we can reach R6 via this path. This will cost us just 3 units. This 1 plus 2. But if we go through here, it will take 2. So this is redundant now. Now fourth one has become redundant. So you can try to visualize, even you can visualize and try to see this, and or you can, but better you solve this type of questions in examination, because you might miss some keys. Fine. So these were the questions in GATE 2010 that were asked in the system, that were asked on distance vector. Now let's see the next question. If you have any doubt, you can write about that in comments, and I will go to the comments. Let me check if there is any problem in comments, and everything is going fine. Yeah, I think everything is going fine. And someone said just hi, hi, someone. So yeah, we will start with our next question. So this question was asked. This one is just a recent question that was asked on this routing algorithm in 2021, Computer Science 2021, and it was question number 25. So what is written in this question and what has been asked? So question is like this. Consider a computer network using the distance vector routing algorithm in its network layer. So they are giving us this distance vector routing algorithm is being used. Now the partial topology of network is shown below. So this is the topology that has been shown below. So you can try to see that they are giving a node R, and then R is connected with X, Y, and Z. X, Y, and Z are neighbors of R, and this X, Y, and Z are somehow connected to Q1. They are not exactly telling us the path, but these are connected somehow. So they will have maybe some path, all three will be having some path with Q and P. Somehow they are connected, Q and. So this is the topology. Now let us see what else is given. The objective is to find the shortest cost path from the router R to router P and Q. So objective is to find the shortest cost path from R, this R, to P and Q. R to Q and R to P. We need to find the shortest path, R to P and Q. What else is given and asked? Assume that R does not initially know about the shortest routes to P and Q. Assume that R has three neighbor routers denoted by X, Y, and Z. So R has these three neighbors X, Y, and Z that I already told you. During one iteration, R measures its distance to its neighbors X, Y, and Z as 3, 2, and 5. So it is also given that these links X, Y, and Z are costing us 3, 2, and 5. These links that are given in the question already, the neighbors of R are connected with a cost of 3, 2, and 5. Fine. This is also given to us. Now router R gets routing vectors from its neighbors that indicates that the distance of to router P from router X, Y, and Z are 7, 6, and 5 respectively. So try to understand once more. Router R gets routing vector from its neighbors. R is getting routing vectors from its neighbor. Who are the neighbors of R? The neighbors of R are X, Y, and Z. So R is getting R is getting distance vectors from X, Y, and Z. And what are they telling? That they are telling that in this routing vectors, they are telling that P is at distance 3, 2, and 5 from us. So they are telling that P is at distance 3, 2, and 5 from us. This X, Y, and Z are telling R that P, Q, and are at distance 3. P is at distance 3, 2, and 5 from us. Now, again, one more thing. Let us try to solve this question here itself. Let us not jump into the previous and next part. Let me take a yellow pen. It is more visible. So once again, let's try to build a topology by ourselves. So R is given. R is connected with X, Y, and Z, or Z, whatever you say or prefer. And X, Y, and Z are at distance 3, 2, and 5. Now X, Y, and Z send their distance vectors to R, and they are telling that they are connected with P with weight that is required, which is equal to what? 7, 6, and 5. So they require this much weight to reach P. Also, they are telling that they can reach Q with what weight? This, the next line that is given. The routing vectors also indicate that distance to router Q from X, Y, and Z are 4, 6, and 8. So distance to Q is 4, 6, and 8. Fine. Which of the following statement is are true, correct, and false with respect to R after the updation of table? So now let us before seeing the statements, let us try to find the minimum distance from R to P and Q. So what how will be the distance to P calculated and Q calculated from R? So it is simple. We get distances from X, Y, and Z to P, and we know distance of X, Y, and Z from our router itself, that is 3, 2, and 5. So what will R do? R will try to minimize its distance to P. So it will try to sum these two values, these two values, these two values, and take their minimum. So what is the sum of these values? So for P, the value it gets from X, in order to reach P via X, it will cost him 7 plus 3. 7 plus 3 is 8, 9, 10. 10 units. From Y to reach P, it will require 6 plus 2, 8 units. And from Z to reach P, it will need 5 plus 5, 10 units. Fine. So this is the thing. And what it will choose? It will choose 8. And because it is choosing 8, that is the path via Y, it will update in its table the next hop for reaching P as Y. Next hop value as Y, and distance as 8 for P. Let us also solve this for Q. So again for Q, what happens in distance vector algorithm? In distance vector, we are getting distances of some nodes from our neighbor, and we try to minimize that distance. So again for Q, what we can do is just take this values, and we need to sum it with the distance of our neighbors and try to take the minimum value. So what will be the values that we will be getting? So for reaching Q from via X, for reaching Q via X from R will cost us 4 plus 3. 4 plus 3 is 7. The second via Y, how much it will take? 6 plus 2, 8. And via Z, what will it cost us? 8 plus 5, 13. Fine. So what is minimum here? We can see minimum is 7. So for reaching Q, we will be requiring minimum 7 units, and that is via next hop, that is X. So this is what we solved. Fine. Now let us see what are the statements. The statements that are given is the distance from R to P will be stored as 10. So R to P is stored as 10. So R to P, I think it is 8. So it is not correct. The distance from R to Q will be stored at 7. So yeah, R to Q, yeah, minimum distance we found out is 7. So this one is correct. The next hop router for a packet from R to P is Y. So for R to P, what is the next hop? So R to P, we see the next hop is Y. So it is what is telling R to P is Y. So yeah, this one is also correct. The next hop for packet R to Q is Z. So what is R to Q? R to Q is X with distance 7. It is not Z. So this one is also wrong. So only options B and C are correct. So yeah, that was what I explained you, and that is what it is written here. You can also go through it, go pause this video and go through this text if you do not understand my explanation. But still, this was the best that I can do. Fine. So let us see the next question. So if you have any doubt, you can bring it, or I can see the comment. Let me see the comments, or I can continue with this question. Yeah, Umesh, I cannot understand what you are asking. Add ANSYS and solid works. I don't know. Solid works, I don't understand this. Maybe you are asking for anything about civil engineering, solid or something. So yeah, Geeks for Geeks is, I think, mostly for computer science. Fine. If you have any other doubt, you can post it in comment, or else we will continue. We will start with this question. So the question that is given to us is this. This was asked in GATE CSE 2014 question, and it was just a 1 mark question. But yeah, you cannot ignore this 1 marks question, because this also ultimately creates a huge impact. So what was the question? The question asked was this. Consider the following three statements about link state and distance vector routing protocols for large network with 500 nodes and 500 nodes and 4,000 links. So these are the nodes and edges, count of nodes and edges. So these are the three statements, and let us see what are the statements and see what are, if they are correct or not correct, and that is what was asked in the question. So let us go one by one with the solution or the statement. The statement one tells us is that the computational overhead in link state protocol is higher than in distance vector protocol. So this is given in statement one, that we require more computation in link state protocols than in distance vector protocol. Second statement that is given is a distant vector protocol with split horizon. So they are removing the disadvantages of distance vector. So this distance vector protocol with split horizon avoids persistent routing loops, but not a link state protocol. So they are telling that this avoids persistent loops, but link state protocol does not avoid loops. But I don't think so. Let we will see the answers. Let us just read the statements first. Third statement is telling that after topology change, that is something is changed, a link state protocol will converge faster than distance vector protocol. Fine. So these are the three statements given. So yeah, let us see which are true and which are false. So the computational overhead, yeah. So computational overhead in link state protocol is higher than in distance vector protocol. So let us just try to quickly revise what was distance vector protocol and link state protocol. So distance vector protocol, what we do is we transfer our distant vectors among our neighbors. So there is just transaction within neighbors, and we try to find minimum distances with help of this transactions. But in link state protocol, we need to do flooding. We need to do link state protocols. We need to flood our link state packets. The link state packets are flooded in our network for each router. So what happens is this link state packet are having much more data than the distance vectors. Here what we have to do, we just have to take minimum distances from this distance vectors. We here try to minimize our distance just from the vectors that we receive. But here we what we do is we flood our network with link state packets, and after flooding we try to do, after flooding our packets, we try to generate the graph at each node. We try to generate our network topology. Try to recreate our network, what actual was our network at each node. And even after generating our network, we track, suppose we have generated, we are node S1, and we generated this network at our end with the help of this link state packets. Then we go for Kruskal's algorithm, sorry, Dijkstra algorithm, which is single source shortest path, and with help of this algorithm we try to find shortest path from this S1, the current node where we are present, to each and every other node in our system. So this Dijkstra will take processing power, because we are finding single source shortest path, we are finding shortest path. So actually this link state protocol will have higher cost in terms of computation. In what happens in distance vector, it just exchange the distances with each other, and it just take minimum values. So here not much of recreation of network topology, and this algorithm dastra is applied, nothing is done in distance vector. But in link state this all are done. This frames, this graph creation and dastra is applied, hence computational overhead. Sorry, what happened? So hence the statement 1 is, I think, correct. Now statement 2, what is statement 2 telling? That distance vector protocol with split horizon avoids persistent loops. So yeah, this is what happens, what was the major problem in distance vector? That was the major problem in distance vector was count to infinity problem, or count to infinity problem, in which if any link broke down, then the what actually happens is its neighbor will get to know about the broken link, but it will try to find a value from the different neighbor that it is connected, and this way the actual infinity value that has to reach other neighbors, that has, for ideal case, the disconnect after disconnection, the distance value infinity should have been reached in a minimum time, but it takes very long time to reach this infinity. It will go on 1 2 3, and it will go on counting value. So it solves this problem, it avoids persistent loop, but not a link state protocol. No, in link state protocol there is nothing such problem, there is no such problem like count to infinity or split horizon is needed. The link state protocol do not have any such problem, so this statement is false. After topology change, a link state protocol will converge faster than distance vector protocol. Yeah, this is true for sure. Distance vector will always it means it will take n minus 1 steps to converge, but link state protocol will just, after flooding, it will converge, and in maximum cases it will converge faster than distance vector. So yeah, this statement is also true. Though so statement S1 and S3 are true, but S2 is false. So that is our correct answer, option D. Also, we will try to see the explanation that it is written here. S1 is clearly true as link state all nodes compute shortest path in whole network graph, that I explained to you. S3 is also true as distance vector protocol has count to infinity problem, converges slower. So it has count to infinity problem, so it converges slower, but link state protocol do not suffer from any of the problem. S2 is false. Why S2 is false? In distance vector protocol split horizon with Poisson reverse reduces the chance of forming loops and use maximum number of hops to counter count to infinity problem. This measures avoid the formation of routing loops in some all, but not all the cases. Yeah, so I think that there is some ambiguity in this statement, but still, the thing is, this Poisson reverse is not in syllabus of gate. It is also a thing that distance vector takes, but yeah, this was all that I explained. This is also correct. This explanation, you need to go with this one. Fine. So let's see our next question. So the next question is this. Try to read this question, and I will see if there is anything in the comment. So yeah, people are asking to make another GFG channel for mechanical and aeronautical classes. So yeah, I will talk with our mentors and let you know people if we can do that. Right. So next question. This question was asked in GATE Computer Science 2011. It was question number 52. So this question asked is C. Consider a network with 5 nodes N1, 2, and 5 as shown. The network uses a distance vector routing protocol. Once the routes are stabilized, the distance vector at different nodes are as follows. So this uses the distance vector algorithm, and these are the final distance vector that are being finalized after the convergence of distance vector protocol. So you can try to see the distance vector. If for n1 node, the first the so one more thing you need to keep in mind that what I told you, or what I explained you previously, or if you have even not watched my previous videos. So what I explained to you is that the distance vector table is created in such a way that the table is created, routing table at A, every table at A is created such that the first thing is destination, the second is distance vector, and third is next hop, NH, next hop. So these three things are present at each node. And in this distance vector, the distances are present. So they are just telling us the distance vector. They are not providing us the next hop. They are not providing us the destination. But you can try to understand the next hop, the destination are always in the order. So if n1 is given and zeroth entry is present at first position, so this is n1, and then n2 is given and zeroth entry is present at second, so it is n2, and so on. So these are the distances to n1, n2, n3, n4, and n5 respectively. The next stop is not provided. So these are the distance vector. From n1 to n1, we will occur zero cost. From n1 to n2, we will have one cost. So you can try to see that in figure. This link is of one cost that they are talking about. So it is not an arrow here. So these are the things, distance vectors, that are given to us in the question. Now let's see what they are actually asking. So in each round, all nodes exchange their distance vector with their neighbors. So that is what in distance vector actually happens. Every node exchange its distance vector with every other neighbor of itself, and then after exchanging the data with its neighbor, it try to minimize its own distance vector. Then all nodes update their distance vector in between two rounds. That change Any change in cost of a link will cause two incident nodes to change only that entering their distance vector. Fine. So they are explaining what happens in distance vector algorithm. The cost of link n2 and n3 is reduced to 2 in both directions. So yeah, that here the main question starts. So what is the main question? The cost of link n2 n3 reduces to 2 in both directions. So these are the actually links are not having any direction, so it doesn't matter. After the next round of updates, what will be the new distance vector at node n3? So what they are actually asking in question is, they are telling us that this distance is being reduced to 2. Initially it was 6 and now it is reduced to 2. So they are asking now what will be the new distance vector at n3? Distance vector here. So this is the question. Distance vector at n3. So what was the initially distance vector at n3? So the initially distance vector that was given to us at n3 was 7, 2, 0, 2, 5. So what will it say? It will say that n3 to n1 is costing us 7 units. So how can we reach n3 to n1 in 7, and that is optimal? So basically what the path we were taking is, you can try to see from the graph itself, is for reaching n3 to n1, the minimum cost is n3, n2, and n1. That was costing us 2 plus 1, that was costing us 6 plus 1, 7. If we go through another path, that is n3, n4, n5, and n2 and n1, it will cost us 2 plus 3 plus 4 plus 1. So it will cost us 4 plus 2, 5, 6, 7, 8, 9, and 10. It is not minimum. So initially what we were taking for n1 to n3, we were taking this path, n3, n2, n1. And for n2, we can directly go to n2. For n4, n3 to n3, it is 0. For n3 to n4, we can directly go, it is our neighbor and cheapest, that is 2. And for reaching n5, we can go by 4 plus 2, 6 distance, 4 plus 6, 4 plus 2, 6 distance. So yeah, that was given in the question. 6 should have been present. Yeah. So it was given to us in the question 76026. 76026. It is not, it was initially 6. 76026. So initially it was 6. 7, first of all to reach n1, 7, 6, then to reach n2, 6, then 0 for itself, then 2 for n4, then for n5 it is 2 plus 4, 6, 760 and this fine. So what are they asking us now? So actually, let's try to jump in the question that they are asking. Let's not confuse other things. So the cost of link N2 and N3 reduces to 2 in both direction after the next round of updates. What will be the new distance vector? So now they are asking us is that the distance vector is the distance is reduced from 6 to 2. Now what will be the new distance vector? So we can see that when the distance is reduced to 2, what will happen is N3 will exchange the distance vector from its neighbor. So when N3 will change the distance vector from its neighbor, it will try to minimize other distances. So initially one was at distance what? One was at distance 7. So you can see N3's distance vector was 76026. 76026 was initial. So now it gets to know that this link has and N2 will send him a new distance vector, its distance vector, but now he will get to know the distance is reduced. That is from 6 it has become 2. So initially as it was 6 plus 1 7, it will become now 2 plus 1. So distance to N1 will become 3. This entry will become 3. Fine. And then what again will change? Now N3 to N2, initially it was 6, so again this will also change. From 6 it will become minimum, that is 2. So 3 2 is fixed. Now 0 is also fixed, distance to itself is fixed. Now the next thing, the best you can do to reach N4 is also 2. It will also not change. Now the next thing that is that will also change is distance to N5. Now N5 was initially 6 plus 3 something, or 4 plus 2 6, or 6 plus 3 9. So it was 6 initially, 76026. But now as this 6 is reduced and it will receive distance vector from N2. N2 will tell that from N2 I have part to N5 and the cost is 3, and the cost is 3 from N2 to N5. And what is my cost to N2? And N3 to N2 is now 2. N3 to N2 is 2. So what is minimum now? 2 plus 3 is minimum. Yeah, so 2 plus 3 is minimum. Then the previous entry. Previous entry was what? It was with the help of this N4, that was 6. So now the last entry will also become 5. So this is the new distance vector. 7 will be replaced with 3. 6 will be replaced with 2. 0 will be 0. 2 will be 2. And 5, 6 will again be replaced with 5. 3, 2, 0, 2, 5. So A is the correct answer. Fine. So yeah, is the correct answer that I explained it to you. It will try to update. So the main thing that happened is the distance vector will be same. The distance vector that N2 will send to N3 will be same. What was the distance vector for N2? The N2's distance vector was 10673. Fine. So N2 will send 10673. But the distance to N2 has been reduced. So initially what was happening, we were adding 6 and trying to find minimum distances. And what was the distance vector from for N4? So N4's distance vector was 87204. So 87204. Fine. 87204. So this was distance vector from N4 and this was distance vector from N2. Now N2 was a distance to N2 is 6. N3 N2 is 6. And N3 and 4 is 2. Now what happened? We add these distances and we can see 10 and this 7 and 2 9, 2 and 2 4, 0 will remain. So this entry will become 2 and 4 plus 2 6. And here also 6 is added, so 16, 12. So what happens was initially what was happening, this 6 was being added in the consideration. But now as this value changed, so this distance vector that we are receiving from this side will give us lesser distances. Fine. So we will try to minimize it and you can find it by your intuition also. So that was all for this question. Now again one more question is part of this question. Let us see what it is. Fine. So the next question is also based on this question. After the update in the previous question, the link N1 N2 goes down. So N1 N2 goes down, and also they are telling that continue to that question after the update that previous question is already done. So this we do not need to consider 6 here, we need to consider it as 2 here. Fine. So after the update in previous question, the link N1 N2 goes down. N2 will reflect this change immediately. N2, this link is broken. They are telling that this link went down. This N1 N2, N1 N2 becomes infinity. So after this, N2 will reflect this change immediately and in its distance vector as cost infinity. After the next round of update, what will be the cost to N1 in distance vector of N3? So they are telling that this link goes down and this has been reflected in N2's distance vector. That was N2's distance vector. Suppose N2's distance vector what was N1, N2, N3, N4, N5, N6, N1, N2, N3, N4, N5, and N6. So initially N2's distance vector N1, N2 to N1 was 1, but now it will be reflected as infinite. N2 to N2 is 0 and so on. So they are telling that this distance vector this has been changed at N2. After the next round of update, what will be the cost to N1 in the distance vector of N3? So they are asking that after the next round of update, what will be the distance vector of N3? So now the thing to note here is that they are telling us that after the next round of updates, they are not asking us after the convergence of the algorithm or after n minus 1 step. If they will ask us about convergence, so that after the algorithm converge or after n minus 1 steps, total number of nodes minus 1. Then as we can see that N1 was connected with the network with this link N1 and N2. And if this link broke down and there is no way to reach N1. So if they told us in question that after the convergence, what will be the distance vector of N3, the cost to N1. So they are asking, actually they are asking us the value of distance vector, that is N3's distance vector, what will be the entry for N1. So actually what is the cost to reach N1 from M3, N1 from N3. So if they will ask us about the convergence state, then it will be definitely infinity because there is no path to reach N. There is no path possible. But they are just asking us for the next round. So they are asking us for the next round of update. So in the next round of update, what will happen? So see, what will happen is N2's vector will change to N2. What will have N2? N2 will have infinity for N1 in its distance vector. But everyone will not update that immediately. What will happen is N4, what we have to talk about, we have to talk about N3. So N3 will receive infinity from N2 for N1, and N3 will receive from N4. N4 will tell that in order to reach N1, what was the best part to reach N1? So N1 was able to reach N4 in 4, 5, 6, 7, and 8 steps. This is 8 and 6, 7, 8, 9 steps. So 9 steps are required from N4 to reach N3. So I don't think we have to consider this change here. So yeah, in the next round, N3 will receive distance from N2 to N1 as infinite. It will tell us that N2 to N1 is infinite, but it will receive distance from N4 to N1 as 8. Fine. So how it will receive this thing, because N4 has not yet received the change that this link is down. N4, what will N4 tell us? Before this link was down, the minimum distance from N4 to N1 was 8, and we will receive that 8 now. So what will happen? It will try to find the minimum value. So it will get N3 will get from one side and 8 from one side. And in order to what are the distances? The distances to from N3 to N2 is 2, and N3 to N4 is also 2. So it will try to fit in the best value. The best minimum value is 8 plus 2, 10, not infinity plus 10. So it will keep the value as 10. That's it will keep N3 N3 to N1 distance as 10. So now that is what we call it as count to infinity problem. It does not directly, we cannot know about the change directly. It propagates slowly, and also it does not converge faster. These are the disadvantages of distance vector routing algorithm. Fine. So yeah, that 8 from 8, where did this 8 come? So you can see this distance vector for N4 was 87204. It was given in question. So distance vector from N4 was 87204. 87204. It was given in question. So it was given in question that from N1, N4 to reach N1, 8 was the distance. So N3 will receive 8 from this side, from N4, and from here N2 instantly knows because it is just the immediate neighbor of N1. So one side it will receive 8 and one side it will receive infinite. So it, and what is their distances? Their distances is 2. So it will try to minimize distance, and in plus 2, 10 will be the answer. So that was the solution for this question. Now we will move to the next question. It is one of the most important question. And after that, there will be some simple questions. If there isn't doubt, you can ping it in comments. Yeah, if you are in doubt, you can ping about doubts also in the comments. I will try to answer them. So yeah, let's move on to discussion. It was asked in GATE IT 2005. So it was question 85A. So actually what happened is there were two parts, 85A and 85B, and they both were related questions. So you need to attempt, if you can do one question, so you can follow on to the next question. So sorry. So the question was, consider a simple graph with unit edge cost. So each edge is one unit costing. Fine. Each node in the graph represent a router. Each node maintains a routing table indicating the next stop to be used and to relay packet and cost to path to destination through that router. So they are maintaining table that we do. Initially, the routing table is empty. The routing table is synchronously updated as follows. Each updated interval, 3 tasks are performed. A node determine whether its neighbor in the graph is accessible. If so, it set tentative cost to each accessible neighbor as 1. Otherwise, cost is infinite. From each accessible neighbor, it get cost to relay to other nodes via that neighbor to the next hop. Each node updates its routing table based on the information received in the previous 2 steps. So actually, what this all is written is, they are telling us that we have a network and we are performing distance vector algorithm in the network. So DVRT, distance vector routing. So they are not taking the name directly, but they are telling us every theory. They are explaining us the whole theory behind distance vector algorithm, and they are telling that we have a graph with each edge that is costing us 1 unit, and we are applying distance vector algorithm. Fine. So that is what is written here. And then what are the questions? For the graph given above, possible routing tables for various nodes after they have stabilized are shown in the following options. So they are telling us that the possible routing tables for various nodes are have been shown. Tables, now this is added by me something. Tables were given for A, B, C, and D with some errors. You have to choose the correct one. So what happened, what was given in the question in the examination was, they had given this graph and they had told us that the algorithm has converged, the stabilizer converged. So what does this mean? They have reached the optimal state, or the algorithm has run successfully for n minus 1 time, and now they have final distance final distance vector at each node. Final distance vector at each node. Final distance vector. So now they were giving us distance vector of few nodes, and they were telling us that to choose the correct distance neighbor. Some tables were having error. Some were having errors, and we have to choose the one which was not having any error. So what we will do is, I am writing the table that were given here in the question. I wrote these tables that were given in the question, and we will try to verify these tables, right? So just a second, let me maintain the more spacing so that it will be better for us to write. Yeah. So yeah, let us try to see. First of all, these 4 options were given. So suppose this was A, B, C, and D. These were the options given. Now, how can you check? First of all, you can see which distance is 0 or infinity. So as you can see here, after A, the dash is given. So this is talking about the table of A. So from A, what it is telling that A to B's distance is 1 and C's distance is 1. So you can see A's immediate neighbor are B and C. So their immediate distances will be 1 if they are correct. Now A to D distance it is telling us is 3. Now you can see to reach D, from A to D, we do not require three steps. We can just reach A to D via A to BD or A to CD or even A to ED. Minimum is two steps. We do not require three steps. So this entry is wrong. So this table itself is wrong. Fine. And even the other entries are also wrong. They are telling that in order to reach E from A to E is 3 units. But here again, A to E, in order to reach A to E, we can go through A to C, then E. And this is also 2 units. So this entry, let us rectify this entries also. So this entry will be 2, correct entry will be 2, and A to D can be reached from B, fine, with 2 units. A to E can be reached with distance 2 via C. And this entry A to F will also not require 4 but 3 steps via C, B, anything is 4. Now let's see the other table. So you can see the entry for C is dash. So this is the routing table for C. So now for C, C is having one distance from A. Yeah, this is correct. C is immediate neighbor of A. C is having one distance from B. Yeah, this is also correct. C is immediate neighbor of B. C is having one distance from D. This is also correct because they are immediate neighbor. C is having one distance from E. This is also correct. C is also immediate neighbor of E. C is having three distance from E. F. So three distance is not possible from C. We can reach C to F just by C, E, and F. C to E to F. So only two edge widths are required. Two edges are required. So this entry is correct. So this table is wrong actually, and the correct entry, the entry should have been 2 here. Third table, you can see it is routing table for node B as B's entry contains dash. So B to A distance is 1. Yeah, that is true. B to C distance is 1. Yeah, that is also true. B to D distance is 1. Yeah, that is also true. Now B to E distance is 2. So fine, B to E we can reach in minimum 2 steps. We cannot reach in less than 2 steps. That is via BCE or BDE. So they are telling BCE, that is fine. The next stop is now B to F is 2. B to F is also 2, and we can reach B to F in 2 steps via BDF. So that this is also 2. So this table is correct. So the table for B is correct. Let's also try to rectify table for D. So what is a table for D? They are telling this table is, first of all, this table is for D. So D is our node from for whose table we are talking. So D to A, they are telling that D to A is distance 3. So this entry itself is wrong. 3 distance is not there. D to A is just 2 units. That is DCA. We can reach B to A by 2 units, and that is D to C and C2. Now D to B is 1. This is correct. D to C is 1. This is also correct. D to D is 0. D to E is also 1, and D to F is also 1. So on, yeah, only this entry. So yeah, that was the answer. This table is correct. Option C was correct. Again, one more question that was continued for this same graph. The graph was given and they are telling us that continuing from previous problem, suppose at time t when the cost has been stabilized, the node A goes down. So they are telling us that this A goes down. This goes down. The cost from node F to node A at time t plus 100 is. So at time t, this A went down. At time at t equal 0, this A went down. So they are asking at t equal 100, what will be the distance of A from node F. So what will happen? Initially distance from F to A, what was the value of F to A? So you can see that F to A is minimum 2. So F to A distance was 2, and minimum the next stop for F was D. So what we can do is we can try to visualize something here. We can see that A is connected, then C is connected, then D is connected, then F is connected. And what is the distance vector for A? Distances for A in their vector. So C was at distance 1 from A, D was at distance 2 from A, and F was at distance 3 from A. Fine, 3 edges are required. Fine. So what will happen now? Now A went down. So C will get to know about this. So C will update his value is infinite. Now this 2 and 3 are not aware of this, and now after the first round of exchange, they will exchange these distances, distance vectors. And what will C receive? C will initially have, C was having infinite distance, but C received, they do not draw. First thing to note here is that split horizon was not implemented. They do not told us anything about split horizon, so we need to ignore that. So what will happen here? C will receive 2 distance from D. So C will receive that D is having a path which is two distance from itself. So what will it do? It will add one for this h cost, and it will store that. So it will say store that C is having distance of A as 2 plus 1 3 units. Instead of infinity, it is storing 3. Now what has D received? D has received infinite from C and 3 from here. So it will what it will do initially, it will so fine, I had written it here. So initially what was there at t equals 0, it was 1 2 3, fine. Then it becomes 1 2 3. After that it becomes 3 2 3, fine. So let me again start it here in neat way. So this was A, and these were the three nodes connected with it, C, D, and E. Now A got down. So C has stored infinity, but what will happen is 1, 2, and 3. It will try to get store the minimum path. So in it will exchange these distance vectors, and then what will happen after the first round of exchange? It will become 3. So first it will get 3, 2, and 3. And after this round, what will happen is they will keep on exchanging their values. So what you can see is this will become now from 3 to 3. It will become 3, and why it will become 3? Because it will receive 2 from this side, and then 2 plus 1 become 3, and this receives what? 3 from both sides, so it will become 4, and it receives 2 from here, so it will become 3. So this is the sequence that you will form: 3 4 3 5 4 5, and this will go on like this. So you can see here that in every two steps, the distance of f was 3 3 3, then 3, then it became 5 5, then 7 7, then 9 9. So initially it was at t equals 0 to step. So it was 3 3, then 5 5, then 7 7. So in every two steps, the distance is also increasing by 2. So you can see that approximately linearly increasing. Fine. And there is no concept of infinity. They have not explained us what is the max value it can reach. So they are asking us simply that what will be its value at time t plus 100. So it will be greater than 100 but finite is really the answer. Fine. So here I have explained it. In every two time step, we can see the distance increase by 2. So t plus 99 where distance from f will be 101. T plus 100 also distance from f will be 101. So this 99 and 100 plus distance will be 101. So option A is correct, and phenomena occurring here is called the count to infinity problem. Fine. So that was this question. We have just a few questions remaining, and we have also, I don't think much left. Yeah. So let's try to see the next question. Consider the following statements about routing protocols and this RIP and OSPF. So RIP uses distance vector protocol. RIP uses UDP. OSPF are sent using TCP, and OSPF operation is based on link state routing. Which of the following is correct? So you need to remember that RIP distance vector uses RIP, DVR, RIP, and this is how you can remember. I remembered it this with DVR, RIP, DVD RIP, or DVR, RIP, and LSP, link state LSR, OSPF. Also, RIP uses UDP. You need to remember this thing. So by this facts, RIP uses distance vector routing. RIP packets uses UDP. Fine. So option 1, 2, and 4 are corrected. OSPF are sent using TCP. This is not correct. You have to remember it. We cannot. We will talk about OSPF when we will talk about the actual OSPF operations. But yeah, these two are correct. And OSPF is based on link state routing. So this is also what I told you. Remember DVR, RIP, LSR, OSPF, and DVR uses UDP. And yeah, that was it. Which of the following is correct? So option 1, 2, and 4 are correct. So something is written here. We will go through it. RIP uses distance vector routing protocol which employ hop count as routing method. Also RIP uses UDP. So RIP uses UDP transport layer 2. OSPF uses link state routing protocol, works within a single autonomous system. OSPF encapsulates its data directly into IP packets and does not use either TCP nor UDP. So OSPF does not use any of them. So you need to remember this kind of facts. You need to go through books for these facts. So statement 3 is false and rest other are.
Which of the following is true about IGP interior gateway routing protocol and RIP and OSPF? So RIP uses distance vector routing and OSPF uses link state routing. This is correct. OSPF uses distance vector. It is wrong. Both RIP and OSPF uses link state routing. Wrong. And both RIP and OSPF uses this is also. So this you can see this based on this fact, these two questions have been asked in 2017 and in 2014. So this is nothing but you have to remember this fact that link state routing and DVR is related to link state routing and OSPF is related to link state routing. Fine. So also these things that I just that RIP uses UDP and OSPF does not use TCP or UDP. It does not use any of them. That was about this question. And I think that is enough from my side today. And thank you very much for